Okay, off we go. So let's see, quick reminder, don't forget attendance quiz and all that, right? So there's the code, make sure to get it done. You have less than 2 minutes remaining, so make sure to get that done. And by the way, reminder, I will eventually just stop making these reminder announcements. Anyway, okay, so make sure that you have procedures and habits in place that will ensure that you remember to do the code. Okay, all right, so back to the math. Last time we were talking about linear approximations, and we wrote down this formula that you'll all remember, right? And now I'm going to move along momentarily, but I do want to go back and hit a point that I kind of glossed over last time, which is this is the linear approximation if such a thing exists. We cannot just go around assuming that because we wrote down a function that it has what could in any reasonable sense be called a linear approximation. Right? So in single variable, what we're looking at right here, the answer to the question of under when does a linear approximation of any meaningful sense actually exist? And the answer is real simple. Function just needs to be differentiable. AKA, you need to be able to take a derivative of it, right? So no big deal, nice crisp answer. It's easy to kind of forget about it. Okay, just planting that thought. We're going to come back to that in a few minutes. So this is about where we ended last time, was with the observation that while this is the unique degree 1 polynomial that satisfies these conditions, along those same lines, if I can get this to cooperate, this is the unique degree 1 polynomial that satisfies these conditions, these very analogous conditions. Kind of the same idea. I want my linear approximation to agree with the function in value at the point where you're looking at, and in first derivative. Okay, but how do we say first derivative in a multivariable sense? Well, we got various partial derivatives. Yeah.
Hi, Professor.
Hi.
I wasn't here last week.
Okay.
Sorry, last class.
Yes.
I was wondering, how do you actually fill out this?
Well, let's talk after class. I think the time's up on that anyway. But so talk to me after class. Okay. This is just the analogous idea, right? This is kind of a multivariable version of what y'all have already seen before. Okay. All right, now let's talk about notation a little bit. And if you look at this part of the formula, it's not the whole formula. If you look just at that part of the formula, what you'll kind of notice is it looks a lot like a dot product in the following sense. I have various factors being multiplied by various other factors, and then I'm adding up these products of various factors. My gosh, it looks just like a dot product. That's crazy. Okay, and it gets crazier, it gets weirder. It's like, oh my gosh, look at these blue ones. These blue ones all together are literally the coordinates of an actual vector, right? So this is not just kind of structurally coincidental. We've got an actual vector here, the coordinates of an actual vector, and furthermore, a geometrically natural vector, x minus a, right? So the idea being that a is the point where we're doing the linear approximation, and x is the point where we're evaluating that linear approximation based at that point a. So, my gosh, that's leaps off the page and is very compelling, I think. So, the conclusion that we come to, a reasonable conclusion's the wrong word. The suspicion, I'll say, that we come to is that maybe these factors, maybe these orange factors, are the coordinates of something that's natural also. So, all right, I'm just going to say, all right, well, look, this vector for which these are the coordinates, I mean, I don't know exactly how natural this is going to be right now, but I'm suspicious that it is. I want to be able to keep an eye on this thing, and by the way, it's going to be notationally convenient. So I tell you what I'm going to do. I'm going to give this a name and a notation. We're going to call this the gradient vector. We're going to use this notation right here. It's pretty standard. By the way, do be careful, this triangle that we use to represent this, it's very important that the point be down. If you write the point up, it means something different. So it's got to be a downward pointing triangle. So yeah, we call it the gradient. And right now, just to be clear, all we know about the gradient is that we're suspicious of it. Right? And I guess you could say it's proved itself to be at least notationally convenient in the sense that, and let me clean up the mess here then, it's notationally convenient in the sense that it allows us to take all of this and write it much more compactly, like that. Yes?
Is there any reason that you used G? Like, would you have to do a different function?
Yeah, the only reason I chose, it's a great question, the only reason I chose to use G here is I wanted this to be a generic statement. This is not something that's peculiar to only if you're doing a linear approximation. I just wanted to, so this is a general statement, it's not a peculiarity of this specific function. Is that, yeah.
But in the example, you would be doing the gradient of f, not
Yeah.
function.
That's right. And
okay.
Yeah, absolutely. Yep. Is everybody happy with that? Okay. All right. So for the moment, just notation and suspicion. Okay, so let's do one. Here is a multivariable function and a point at which I would like to write down the linear approximation of this function. And I'm literally gonna plug right into this expression right here. And so let me just highlight for sort of, let's keep our eye on the ball. That's all I'm gonna do is I'm gonna just plug into that formula. So, okay, fine. Here's our function. That's f, into which I need to plug this point. That's our a. So take that point, plug into that function, and f of a is 5. Nothing just happened there. Just plugging in. No big deal, I hope. Let's see. Let's look at this next expression here, gradient of f at a. Well, the first thing I'm going to have to do is I'm going to have to compute the gradient, which again, per this definition, the gradient is a vector consisting of all the partial derivatives. So take all those partial derivatives, make sure you can do that, right? We've already talked about how to compute partials. And then again, I do have to plug in this point, right? The point at which I'm doing the approximation. You've got to plug that in. And then our actual gradient evaluated at that point that goes here is 2, 4. Everybody with me? And then lastly, this thing migrates. Let's see here. Lastly, I got to write down the x minus a factor. Well, of course, a we just talked about. That's 1, 2. So there's the 1, 2. And x being the point where we're evaluating, and so I'm using again this alternative notation that I used in the past, and this interspersed here and there throughout mine. It's just a notation, nothing to be aware of. But anyway, the x vector is x, y. The point again where we're evaluating this function is right there. So this is the x minus a. And there you go. Now, if you were so inclined, and maybe you would and maybe you wouldn't, but if you're so inclined, you could take this, this general formula that we've seen turns into this. You could multiply it out, collect terms, and you could write it like this. And notice it's literally a linear function. Well, in the sense that it's a flat thing, right? It's not technically linear because of the minus 5. Sadly, that word linear gets used in different ways in different contexts. It's unfortunate. And the claim is that this function will do a really good job of approximating this function f, as long as you're really close to that point. 1, 2. Okay. All right. Now, should you do this? Should you multiply it out and collect terms? It depends on the circumstance. In a math class, Most of the time, I don't really see the point. What would be the purpose of that? I like certain things about leaving it in this form. If you leave it in this form, I can see the gradient. I can see the value of the function. There's utility in that, right? I can see the point where it's being evaluated. That's really nice. In most cases, certainly in a math class, just if there's no instructions or motivations to the contrary, why not just leave it like that? Now, if you're in the process of writing a computer program to actually compute, if there's a subroutine or whatever they call it these days, I don't know, that's gonna, where you're gonna need to evaluate this linear approximation like, millions or billions of times, streamline it. For sure. Right? We want to keep things tight. But, pretty different circumstances. How we doing? Okay, now let me come back up here. Notice that we started looking back to single variable. In particular, we had a single input and also a single output. The second thing that we looked at here, we generalized a bit to a multivariable input. Right, so several input variables. So this new formula down here was a generalization, but notice it was still single outputs. So these were, I'll remind you of the lingo, real valued, otherwise known scalar valued functions f. Right. So now we want to consider. All right, let's do the whole thing. Right, let's eat the whole burrito here. Multiple inputs and multiple outputs all at the same time. All right, that's our next question. And here's the answer. And you're going to notice it got a very similar form, very similar structure to what we wrote down in the both previous cases. I'll come back and talk about that in a second. But I haven't told you what this thing is yet, so let's go back up to here. If you look back to this example, I wrote down a long, tedious formula, and then I talked about the way to streamline the notation later. There's too many terms for me to expand this out and show you the long, tedious form. I'm just cutting straight to the compact, efficient way to write it down. And so this expression right here, df, and we'll talk later about what the D stands for. Although I'll bet you could guess. But anyway, let's leave that secret for the moment. This df plays the role kind of that the gradient did in the previous form. Okay. All right. So notice the df matrix consists of a bunch of partial derivatives. It's all partial derivatives in here. But notice as well, they are organized in a very particular, specific way. This is delicate. It's got to be done just so. And if you don't follow this exact pattern, your bridge is going to fall down. Right? So it's very important that you let's note and be careful about the specifics. In any given column, it's all partial derivatives with respect to the same input variable. In any given row, it's not. We're taking partials with respect to a bunch of different input variables. But any given row, it's all partials of the same output variable. Everybody see the pattern there? I'm also going to point out that there's an implied ordering. And whatever is the within Rn, whatever is the ordering of the variables, you have to put those columns in that order. And then likewise in Rm, there's a natural ordering of the variables, and you have to put the rows in the order corresponding to that ordering. So you've got to keep everything in order. Okay, alrighty. So here's the formula. Now, let's make sure y'all are clear on why this works. And the answer, to why does this work, I'm afraid is just a little bit of tedium. I think this is a healthy little bit of tedium. Everyone should do this once in their lives. I did mine. Now it's your turn, right? So I encourage you to do the following. Take a function where there's, let's say, I'm going to say 3 inputs and 2 outputs. Something like that, right? Don't go crazy. And write down this matrix explicitly. And then write down this expression explicitly and multiply it out. Collect all the terms, right? Get that actual function on the page and then confirm that this new function that you've written down indeed agrees with f in value and in all of the partial derivatives. And you just got to write it down and notice that, well, sure enough, it works. Like I say, good healthy exercise. I hope you'll spend 5 minutes on that. How we doing? Okay, let's do one. Here we go. I guess I can zoom back in. So, all right. Well, here's a function and a point, and I'd like to approximate the values of this function. I'd like to do so for points that are near this point 1, 2 in the domain. So here we go, and you'll notice, of course, I've got our formula right there, and I apparently chose to write this in terms of r instead of x. Again, notation, whatever. And notice it's the same thing. The first thing you got to do is take A, plug it into F, right, and whatever you get, that goes there, right? Now, why did I get a vector? Well, because this function is vector valued. All the values are vectors, so you'd better get a vector. That's what it is. Okay. Then let's see, we got to write down the derivative matrix. So here's what the derivative matrix turns into. And again, don't forget to plug in your point, at which point the derivative matrix turns into that which goes there. Just like we did with the gradient. We get a matrix this time. Why? Because df is a matrix. That is what it is. Okay. And then x minus a, same story there. So notice the shape of this matrix is exactly what it needs to be. It has 2 columns exactly as would be necessary to be able to multiply by a vector with 2 entries. Right? It has 3 rows so that when you multiply it by said input vector, you get a 3-element product as exactly as would be necessary to add to the existing value, again, with 3 entries. Everybody on board? So it kind of has to be this shape of a matrix. Okay. All right. Okay, so I'm going to call your attention now to a little pattern that I don't think I observed previously, and this again is just a eyebrow raiser. But notice the derivative. Well, here, let me do it like this. The derivative. Notice where the derivative is in the form of this linear approximation, and then let's ask the question now. Okay, well, for our next version here, for our next version of the thing, what is it that's playing the role analogous to the role that the derivative played? And you'll notice it's the gradient. That's the thing that's playing the analogous role. There is a case to be made there that, well, apparently the gradient is kind of playing the role of a derivative. Maybe a gradient is a kind of a derivative of sorts. Does that make sense? I mean, previously we've been thinking of the only derivatives we've actually defined up to now were partial derivatives. Now we've got a vector that in its different way is kind of, again, playing the role kind of like a derivative. How about that? And now let's go up to the vector valued multivariable case, and notice the thing that is playing that role is this matrix, the DF matrix. It is in this multivariable vector valued setting. It's the thing playing the role of the derivative. Maybe we should think of this matrix. Weird idea. Think of a matrix as being a derivative, but maybe this is something we should think of as being kind of a derivative. And by the way, that is what the D stands for. Which, again, I think you probably guessed. Is everybody on board? Everybody happy? Okay. All right. Okay, I've already made half of this observation here, but again, you notice all the elements of any given column, they're all partials with respect to x1. So I'm going to note that one way to say that is that column itself is the x1 partial of the full function, the vector valued function f. Right? Reasonable notation. And now, this is something I did not previously note, but if each row is all the different partials of a given output variable, this top one, for example, f1, we already have a definition for that. That's the gradient. Right? So neat fact, derivative matrices have rows that are just the gradient vectors of the component functions f1 through fn. So derivative matrices are made up out of gradient vectors. Kind of cool. And then a little bit of terminology, frustratingly, they call L the linear approximation, but it's not linear. Right? It's, in this annoying sense. I mean, it's linear in the sense that it's intended, I suppose. But is L a linear transformation? No, it is not a linear transformation. So awkward. But DF, being a matrix, is literally a linear transformation. And depending on how you think about the semantics, and this could be argued to be maybe why they call L linear, because the thing that's doing the heavy lifting in that function is literally linear. I saw a hand somewhere. Yes?
What does affine mean?
It's just a word. Yeah, affine, it means that it is a sum of a linear function and a constant. Or I guess, let's see here, I'm not sure if that's strictly the definition, but anyway, it's equivalent. It's a constant plus a linear transformation. Yeah. But you don't need to know. This is just kind of a cultural point in case you're curious. Okay, moving along. Okay, flashback, old news, nothing new here, I hope. The only thing that's new here, I suppose, is how we're going to view this. In single variable calculus, when you already knew everything on the screen at the moment, every picture we draw is a graph. What do we need to focus on it being a graph? And I'll bet you that in your single variable calculus experience, there was probably a fair amount of conflation of linear approximations and tangent lines. You know what I mean? Like, I'll bet you've heard people say stuff like, well, the linear approximation is just a tangent line, or it's the formula for the tangent line, or sloppy statements like this. We can't afford to be that sloppy at this point. Again, we've talked about how not every picture we're going to draw is a graph. You got to be explicit. When you relate algebra to geometry, you got to be explicit. What's the nature of that association? How are you connecting these things? And there's different ways to do it. So specifically, we have this thing called a linear approximation. We've written down this formula right here. Single variable, so this is just a function of x. Notice when we wrote down the definition of a linear approximation, no y's. Right? This is a function of x, and this is the formula for how to compute the output values. End of story. Right? So here's the thing. We can talk about the graph. And how do we form a graph? Well, you choose to give the name y to the output values. Right? And again, not conflating L, which is a function, with y equals L, which is an equation for the graph, not the same thing as a function. Everybody see the distinction? And I know it's fussy, right? Is everybody with me? So the graph of the linear approximation is the tangent line. And this is what people are trying to say when they say that the tangent line is the linear approximation. They're just being sloppy about it. Okay. All right, so again, hopefully old news. And that sets the stage very nicely for us to make the same or analogous observation for a multivariable function. Here's our linear approximation. We've written it down already. Old news. What is this? Well, it's a function. This is not a geometric object. This is a function, right? It's an algebraic object. But we can, again, talk about the graph. We can set the output values equal to a new variable. This gives us the graph of the function. And that graph of the linear approximation, it's going to be a plane. Again, you can probably speculate it'll be a plane because it's first order, right? And in fact, that will generically, wrong word. That will typically, for nice functions of the sort that we're going to be dealing with, that will be the tangent plane to the graph of the original function. Is that cool? Everybody with me? All right. Okay. This is another one of these cases where it makes me sad, but we have to skip a bunch of stuff. If this were Math219 and I had oodles of time, I would love to spend a week talking about differentiability. There's a lot to say. It's really, really, really not obvious. We just don't have time for it, and it's not really quite the purpose of Math219. Y'all are engineers. Ultimately, we have to focus on where the rubber meets the road, right? So, beautiful mathematical discussion, lots of things to talk about. Ultimately, the big punchline of these next two pages is that we get a definition of what it means for a function to be differentiable. And what we mean by differentiable is actually a little hard to describe really in sort of loose terms, but roughly speaking, we want a function where it's gonna look nice. I want it to have a tangent plane, nothing creepy, nothing weird, nothing anomalous, just a nice flat-ish thing where I can draw a flat tangent plane and come on, you know what I mean, right? That kind of thing. And if you get real fussy about it and start writing stuff down, exactly what do you want, this is what you end up with. And you'll notice that it's clunky and not immediately intuitive, right? And the reason that we have to do that is because this is deep water. There are some weird things that can happen. This is not like single variable calculus. In single variable calculus, a function is differentiable if you can take a derivative. That stuff. Not so in multivariable. In multivariable, there's some weird things that can happen. And I'm going to show you an example, and I was going to pull it up before I started the lecture, and then I forgot. So let's do that real quick. Bear with me just a moment. Let's see here. It is in here. Here we go. So this is, that's too big. Okay, that'll work. So what we have here is a little smaller. This is a plot that I made on Desmos. Hope y'all are familiar with Desmos. It's a convenient way to plot certain kinds of functions. The formula for this function is R sine of 3 theta. Nice, simple formula. Easy to write in terms of natural, convenient variables R and theta. I didn't have to do anything creepy or weird it was a nice, simple little formula, right? But let's take a look at this graph. And at first it doesn't look so bad until you think about what exactly is it that's happening at the origin here. Right? And this is super weird at the origin. At the origin, all right, let's put you know what? How about I do this in a darker, yeah, there we go. At the origin, well, as I go in some sense in this direction, I get a nice straight line, nothing seemingly very complicated happening. Right? It's literally a straight line there. And you can plug in, pick your favorite value of theta and plug in, and you'll find that you literally get a straight line, no big deal. But then wait a second. In this direction, I get a straight line. But then sort of in between these two directions, let's see what would be a good contrasting color. Let me see if green will work. In between those two directions, it's going way up like that. Well, what's going on here? Well, what's the tangent plane to this going to look like at the origin? We got a problem here. It doesn't really make any sense, right? This is not smooth in the casual sense of the word. It's not like it's just, oh yeah, we can just put a tangent plane there. This has got this weird sort of up, down, up, down, up, down, up, down, weird sort of thing happening. It's all happening at the origin. And the thing is, in any single direction, it's nothing but straight lines. Right? That doesn't seem like it ought to be scary or bad or weird. The partial derivatives of this function, perfectly fine. At the origin, the partial derivatives are perfectly well defined. But if you try to draw a tangent plane to the graph, you crash and burn. You can't. It doesn't make any sense. Right? So my purpose in showing you this example is to kind of dispel the idea that, well, if you can take partial derivatives, it's all good. It's all fine. No, it's really not. Just the mere being able to take partial derivatives doesn't eliminate really bad stuff like this. And that's why we need this idea of differentiability. Is that, y'all willing to buy that? Okay, so what do we do about it? And by the way, who needs differentiability in the first place? Why don't we just throw in the towel on the whole concept? And the answer is because differentiability is exactly the condition that we need to be able to write down critical theorems that we'll write down later. Okay? But several critical theorems, the exact sharp condition is differentiability. So it's a problem. There is a very nice sort of saving grace on this, and that is a related idea called continuous differentiability. It's not the same as differentiability. It's a stronger condition than differentiability. Typically, if a condition is stronger, it's harder to check because you have to, there's fewer functions that say you'd think you'd have more things to check if it's literally a stronger condition. Weirdly, it's quite the opposite here. Continuously differentiable is easy to define. So easy. It's like falling off a log. Continuously differentiable just means that the partial derivatives exist. Hey, wait a minute. I just gave you all this big speech about how that's not enough. Continuously differentiable just adds the further requirement that those partials be continuous. And if the partials both exist and are continuous, then you know tremendous information. This easily checked condition in particular implies differentiability. So this is the workaround. If you ever need to know that a function's differentiable, let me rephrase that. When, in the many circumstances that you're going to need to know that a function's differentiable, don't look at the definition of differentiability. My God, that's really hard to work with. It's really inconvenient. No. If you need to know a function's differentiable, in the great majority of cases, you can just check that it's continuously differentiable that will immediately imply the differentiability that you need. Let's see an example of this in action. Yeah, here we go. I'll do it like this. Here's a function. Is it differentiable? Okie dokie. Well, here's what I'm going to do. I make the modest observation that I can compute all the partials. They're all polynomials. That's algebraically obvious. All the partials are polynomials. Polynomials are continuous, old fact. By the way, let me make sure everybody's good with this, and this applies in multivariable as well as single variable. Most functions you're going to encounter, certainly in this class and almost certainly in most classes, a few exceptions, most functions that you encounter are continuous wherever they are defined. So polynomials, logs, exponentials, trig functions, sums, products, quotients, compositions, anything you can make up out of any of these many functions we just listed are all continuous where they are defined. I hear complaints, I'm sure. I can hear the thoughts, right? Hey, wait a minute, tangent has a gross discontinuity, doesn't it? Yeah, where it's not defined. But the great majority of, well, again, all these functions that I just listed and all the things that you can do with them, they're not continuous everywhere, but they are continuous where they are defined. So polynomials are defined everywhere, therefore they're continuous everywhere. Boom, done. Partials being continuous is the definition of continuous differentiability, and our theorem right here tells us that it's therefore differentiable. And no big multivariable limits and clunky, massive expressions to deal with. Very, very quick. Is everybody on board? Yes?
What do you mean by defined?
Yeah, well, tangent's not defined if you plug in the angle to be pi over 2. Okay. It's literally not defined. It's a lot of people get this wrong and say that tangent of pi over 2 is infinity. It's not. Tangent of pi over 2 is meaningless nonsense garbage. There is no such thing. So that's what we call undefined. Is that cool? Yeah. So log fails to be defined. For example, if you plug in a negative value, right? There is no such thing as log of a negative number in the context of doing real numbers. Yeah. Right. Okay. A real quick side note. Hope this is believable, but differentiability being a really strong condition. Every differentiable function is continuous. All right, whatever, who cares? Where this gets interesting is when you turn it around backwards. This is called the contrapositive. I hope y'all have seen the contrapositive construction, right? If P implies Q, then not Q implies not P. So the contrapositive here is a differentiability test. If your function fails to be continuous, game over. There's no way it could possibly be differentiable. And there's an example down here, which I hope is pretty believable. And I don't want to go through the details, but you can see the values of the function are here sort of like this, except then they're 0 down here in the sort of the first quadrant. And you probably notice we have a massive discontinuity there. So that function is not continuous, and that means it is not differentiable. And by the way, I will point out that, again, it's not differentiable, but at the origin, the x partial is perfectly well defined. The x partial is 0. And at the origin, the y partial. How is the function changing as I go in the y direction? Perfectly well defined and 0. Okay. But the function as a whole, not differentiable. Okay, so weird stuff. Let's just kind of shuffle things around a little bit. I want to show you all a really important property of the derivative matrix. I think this is a really big deal. Heretofore, the derivative matrix is a tool that we use to write down linear approximations. Okay? So here's a different way to phrase it. There's our formula. One of the whole purposes of linear approximations is that the value of the function is the same as the value of the linear approximation, so I can rewrite that a little bit. There. And then I can take this term and move it over to the other side of the equation by subtracting. Right? I mean, it's innocent, no big deal. And now let's look at this equation here. And this equation is telling us something really, really valuable about the derivative matrix. The derivative matrix is not just a notational convenience. The derivative matrix is literally telling us what to do to how much I change the input. I mean, that's literally what this is, r minus a. Elsewhere, I think I wrote it as x minus a, whatever. Okay. This talks about how much are you moving the input from where you've done the linear approximation. This is your input change. And the derivative matrix turns that into our linear approximation of the output change. Namely, how much did our linear approximation change? I hope that might ring some semantical bells in y'all's minds. What that means is this DF matrix is literally turning input changes into output changes. That's the definition of it. That's the unifying feature of all derivatives that we're going to talk about. They turn input changes into output changes. So, I think with this in mind, oh, and by the way, just a terminology thing, differential is the term that we use to talk about how much we're changing in the input, and it's the term that we use to represent the linear approximation, right? You gotta throw them in there. Right? Linear approximations don't tell you how much the function actually changes, but our linear approximation to the output change, also called a differential. And you probably recognize that term from single variable. So yeah, input changes into output changes. Really big deal. And by the way, I made some discussions last time, I think it was, that we'll start with partial derivatives, and they're nice in certain ways, but ultimately, when you leave this course, I hope partial derivatives are not sort of what's on your, sort of like, that's not your foundational concept of what a derivative is. That we're going to have a much better thing that really should be, what is a derivative? Your answer, the first thing that comes to your mind when you hear the question, what is a derivative of a multivariable function? This is it. The derivative matrix. In the most general of cases, multiple input variables, multiple output variables. This thing is what turns input changes into output changes. So, by the way, when you're in any, mathematical context and you have some, vector valued multivariable function, when you hear someone say the derivative, they're talking about this matrix. This is what the derivative is, and you kind of just have to get over that. I mean, it doesn't feel right? Isn't a derivative supposed to be a number? Isn't a derivative supposed to be like a slope of the graph or something like that? Not anymore. That's this, there's this narrow, peculiar circumstance of partial derivatives that, again, only makes sense if very strict and weird conditions are satisfied. As a tool, it has its uses. But this, in general, is the thing that is the derivative. It does what derivatives are supposed to do. Enough of that. Okay, so here's a picture, just to be explicit about it. So notice this, the kind of picture that I'm drawing here. This is what I like to call the literal picture. So we have a domain over here on the left. We have a target over here on the right. And in the literal picture, we talk about input points, like that point A. And that input point, by way of the function, turns into this, let's say, output point. Right, and we tend to represent this like so. That's what f does. It takes an input point to an output point. the way the derivative shows up on this picture is that it keeps track of when I change the input, and then there is correspondingly a change in the output. The derivative matrix is the thing that turns the input change into the output change. I think that's a really nice way to think about derivative matrices. It's just, again, just a picture of what we talked about above. How are we doing? Is everybody with me? Let's take a moment to recognize how nice it is to have this kind of picture, right? If we didn't have this idea of the literal picture of a function and put the domain over there and the target over here, we couldn't draw this picture if we didn't have, we couldn't draw this picture if we were fully reliant on graphs. Right? You try to draw this picture in a graph. I can't even draw the graph. The graph would be four-dimensional. There's no way to make that work. Right? So this picture really earning its keep with this example. Yes?
For target, what are the axes values?
It'd be like F1 and F2, I suppose. You could give them names if you want to, but typically, again, we would only give them names if we're going to draw the graph, which we're not going to do. So you don't need to, right? So let's just say F1 and F2. Yeah. Okay. All right. Now, this formula we were just talking about, right there. That's just a recopy. Let's do this move right here. Let's divide both sides by dt. That's all I did here. Just divide both sides by dt. And again, this is not Math219. I don't want to worry about formalities and stuff. But if you just, this is, I would say intuitively, this is a perfectly good, reasonable intuition for what we could make more formal if we were in such a class, which we're not. So we divide by dt. Now let's try to make sense out of this equation here. What does this mean? Well, you would probably be easy to sell on the idea that the rate of change of position is a velocity. We're going to talk more about that. I'm going to be more persuasive about that later, but I hope you're willing to buy that at the moment. Rate of change of position is the velocity of the input, and the derivative of the output value is the velocity of the output point. And so with that point of view, again, let's ask how do I think about the derivative? Well, the derivative is the thing that turns input velocities into output velocities. And again, it's what turns that into that. So, slightly different statement than we had before. Up here, we were talking about how df relates changes, input changes, to output changes, like actual discrete little changes. And this being, of course, a linear approximation. And so that's not quite the same thing as saying instantaneous velocities. So conveniently, same interpretation. And arguably a little bit nicer because I don't have to put an asterisk over here and say, well, by the way, that's just a linear approximation and blah blah blah. No, this is literally exactly for a differentiable function. What you get when you multiply by the derivative matrix is exactly the output velocity of your function. Okay. All right. So I like to dwell on this point. I think this intuition for a derivative matrix is really important. A case could be made that this is the most important way to think about a derivative matrix. It's what you multiply by input, let's say, velocities to get output velocities. And again, 10 years from now, when you're looking back and, oh yeah, I remember being in college. At some point, somebody brings up the word derivative matrix. I hope this is the first thing that pops into your mind. This is what derivatives do. Okay. Let's see. This last little bit is this is just notation. It's ultimately not that big a deal. But if you go through the same algebra that we did for the general case, but if you just do it for this real valued case, instead of writing this as a derivative matrix, remember we can also write this as a gradient with a dot product. Ultimately, it's the same thing. Right? So the punchline then is that the gradient, specifically dot product with the gradient, again, you can make the same interpretation. That's the thing that you do to input changes to get output changes. Be they discrete changes and approximations, or be they instantaneous velocities. Take your pick either way. Right? So, suit yourself. I mean, ultimately, there's nothing happening here. Ultimately, all that's going on is that these are exactly the same. Cannot emphasize enough, for real valued functions. Got to be a real valued function. You can only talk about gradients for real valued functions. And if your function is real valued, that matrix only has one row. Right? So again, this is strictly only for real valued cases. But the punchline is then, the gradient does exactly what the derivative matrix is. In other words, the gradient is what turns input changes of whatever type into output changes of whatever type. And notice, real valued only, so this is just the number line, real number line over here on the right. Everybody good? Okay, we're out of time. Drawing the line right there. Y'all have a good rest of your Monday. See you on Wednesday. And I'll see you later. Okay.
Thank you.
Yeah, no problem. Have a good one. Yeah.